Yeah, thank you very much for the introduction. And let me first of all thank the organizers for the invitation. I'm very happy to have the opportunity to speak here. And it has been a wonderful conference. I've learned a lot of mathematics, and I've had a very pleasant stay throughout the 2 weeks. So thanks a lot. And I hope I will manage to visit again in the future. So, right, as my title says, I should be talking about two things. So, on the one hand, I will explain special value formula for L functions of Hilbert modular forms of parallel weight 2. And in the proof of the main theorem, there is a crucial cohomological input, which is this Ihara's lemma for Shimura curves. And ideally, I wanted to explain the more recent work I'm doing with Karagiani, generalizing the lemma to quaternionic Shimura varieties. But so probably this is actually too ambitious. And so I decided to focus mostly on the first part because it's, of course, much closer to the topics we have been discussing throughout the conference. So if I have time, I will say something about Ihara's lemma at the end. If not, feel free to ask questions. All right. Yeah, so let's go. So because we are approaching the end of the conference, I thought I will start the first 10 minutes maybe with some kind of general overview where I will try to emphasize some key themes that have been recurring throughout the talks several times. So hopefully this will be useful to some of you. And in any case, it will serve me as a motivation to later introduce my main theorem. So yeah, the first 10 minutes will be maybe a bit general and vague. Right, so it's a conference about elliptic curves. So let's start. The elliptic curve E over K, or E is an elliptic curve. For now, K is just any number. All right, then we have the associated L function. Okay, and let me state maybe this version Swinnerton conjecture. So first of all, it tells you that the order of vanishing at s equals 1 of the L function should be equal to the rank of the group of K points, which is of course finite because of Mordell veil. And secondly, there is a precise formula for the special value, which I will denote by L star over K1. So this by definition is the first non-zero term in the Taylor expansion of the L function at s equals 1. And this, well, should be the product of a bunch of things. So there is a period, omega, and there is a regulator. Then there is the cardinality of the Tate-Shavarevich group, which is conjectured to be finite. So this is part of the conjecture. And then you have a bunch of Tamagawa numbers. So here V is a place of K, but these Tamagawa numbers, they are different from one only at places of bed reduction. So here is a finite product. And the denominator, you should have the square root of the absolute value of the discriminant of K. And then the cardinality of the group of torsion points square. So this is the formula, and this is what I will be mostly interested in throughout the talk. And maybe let me add point 0. I mean, first of all, you should make sense of this, and this is already not obvious, so let me just remind it. So this L function, it converges in principle, a holomorphic function on this half plane, but of course, you're interested in the behavior at s equals 1. So first of all, you should know that there is analytic continuation. The complex numbers. All right, and I guess the first thing I want to do is to recall something essentially from the lecture series by Flack. So the point is that there are, as Flack explained, there are at least two ways of thinking about this conjecture. I will briefly remind how to reformulate the the vanishing order part of the conjecture, and will not say much about the formula. So in the first one, historically, is the one that maybe nowadays is not so well known. And it was originally done by Tate in 1965, the same paper where he discusses the Tate conjecture. And it's rather about zeta function arithmetic schemes that Flach discussed. So what you can do, you take E over OK, an elliptic surface, so this should be a proper regular model. Of your elliptic curve, then you can look at its zeta function. Okay, and the order at s equals 1 of these should be the following. So you take the rank of the global section of the sheaf of units minus the same thing with H1. Okay, and of course, this second part here is just the Picard group of the surface. So basically, this is a naive and very special case of what more precise conjectures that Flach discussed. And here, so unfortunately, I will have nothing to say about this viewpoint, but I just wanted to recall it. So what I will instead focus on from the talk is this reformulation to the block KATO. And so yesterday, there was some debate about when this appeared. And of course, so the point is that you can find the paper on Tamagawa numbers of motifs in this volume written for Grothendieck's 60th birthday. So Grothendieck was born in 1928, so the conference was in 1988. But then the volume is published in 1990. But so anyway, what did they do? So let me introduce some notation. So TP of E will be the periodic Tate model. And this sits inside VP of E, which is by definition just TP tensor over ZP with QP. Okay, and then the formula is the following: order of vanishing s equals 1. This L function should be equal to the dimension as a QP vector space of the Selmer group of VP of E. Okay, and of course, right, if you know that the Tate-Chaparich group is finite, then this is equivalent to this point 1 here. And once more, as Flach explained, you can also restate special value formula from this viewpoint. Though I will not do it, but I will tell you later on the precise formula I will prove. Okay, so this is two viewpoints. And as I said, I will focus on this one throughout the talk. So maybe let me give some general and maybe vague idea of how you can approach it. So this block KATO conjecture usually can be approached under quite restrictive conditions for the moment. So let me say only if two things happen. So the first thing is that K cannot be for the moment an arbitrary field, but mostly totally real Gaussian field. Or maybe if you do Iwasawa theory or some equivariant stuff, you can take abelian extension of such. Right, this is the first restriction. And the second one is that results are currently known in a very low analytic range. So that's most one. Okay, and let me tell you why there is such a restriction and what are the key things you need to approach the conjecture, and then you will see them in action in the proof I will describe of the main theorem. So the point here is that usually you always need two inputs crucially. So the first one is that modularity. So you need to know that A over K is modular. By definition means that there exists F, let's say, an automorphic form for GL to K, whose L function is the L function of the elliptic curve. Okay, and why do you need it? Well, first of all, because this is the only way we currently know how to prove this point 0 here. Okay, well, except in the CM case, which was explained by Yuka before. But okay, anyway, so this is currently known, at least potentially, so after a finite extension, if K is a totally real or CM field by this 10 authors paper that appeared in 2018. Okay. And the second key thing is so at some point, you need to understand these special values somewhat explicitly, and this is usually done by the so-called zeta elements. So you need somewhat explicit so-called zeta element, which is related to this special value. Okay, and again, we have seen a lot of examples throughout the conference, so maybe we mentioned two classical ones, which is KATO zeta element. And for us, it will be more important actually, that's Higner points, as I will explain later. And I think this was discussed in great detail in Antonio Lei's lectures. All right, so those are the two key inputs. And yeah, what I will do now is I will state a theorem in this setting and explain how to use these key inputs to actually prove one inequality in a special value form. Okay, so I think this is the end of the introduction. So if there are no questions, I will just state the main theorem. All right, so I will start with the totally real field, F. And I take K, a quadratic CM extension. Okay, then take an elliptic curve E over F, and I assume that it is modular, as I said. Okay, which means in this setting that you can attach to it F. So this will be a Hilbert-Cast form. Well, let's say new form of parallel weight 2. Trivial central character. And rational Fourier coefficient. Okay, and well, actually, the main theorem I will state, it works in this setting, so we don't need to assume the very last thing, but for simplicity of notation, we'll stick to this. But maybe let me remind, in case you don't know, that even if you assume all of this, it is not even known in general how to go back. So if you take a real quadratic field and your n is 1, it's not clear how to attach an elliptic curve to such an object. Okay, anyway, so I assume I start with such an F. And then you have the associated Galois representation that I will denote by rho. With values, well, let's say the integral one will be valid in automorphism of a module that I denote by E of F. So this will just be abstractly isomorphic to GL2 of ZP. Okay, and then if you're here, you can reduce modulo P. And I will denote the reduction by rho bar. Okay. And I think this is everything I need to state the main theorem. So. All right. So I have two assumptions. So first of all, n, my level should be square free. Maybe I forgot to say, of course, this n is an ideal in O. Right? So it should be square free. And for every prime ideal dividing n, I want it to be inert. Okay. All right. And secondly, I'm outside the CM case. All right, those are the assumptions. And what's the conclusion? Then I get the following implication. So suppose that the L function of f base change to k at 1 is non-zero. Then, as I said, you get one inequality in this Bloch-KATO special value formula. Namely, the Selmer group of A of f, the length of the Selmer group as a ZP model. F is at most the periodic valuation of the algebraic part of the special value. Okay, and this will be true for all but finitely many. Primes P. Okay, maybe let me write it here. So here, as before, V of f, V of f, tensor QP, and A of f is V of f, modulo T of f. All right, so this is the statement. So there are no questions about the statement. I will.
But finitely many, it's somewhat explicit.
Very good question. This is my first remark here. Good catch. Thank you. So yes, of course, like this algebraic part of the special value will be a unit for about finitely many. But yeah, the first remark is that yes, I wanted to state the theorem as quickly as possible. Then yeah, in the paper I wrote something more precise. So maybe let me say it. You can actually give some explicit condition. On P, and maybe I want to mention at least the two most important ones. So actually, you will need that P is bigger than 3, and you will need a big image assumption. So the image of this residual Galois representation must contain SL2 of FP. Okay, and then there is a third, more technical condition that I'm not stating. All right, then other remark. In fact, yeah, you can actually prove more, but again, for the sake of time, I will not state everything. So let me just say that you can establish a similar statement in rank 1. Namely, you can establish an upper bound for what? So for the length ZP module of this Selmer modulo the divisible part in analytic rank 1. So when the first derivative doesn't vanish at 1. Okay, and I will not have time to discuss this, but maybe one interesting point is how do you do it? You actually reduce the rank 1 case to the rank 0 case, which is kind of interesting phenomenon. So this is reduced to the rank 0 statement. And the basic idea of how to do it, I learned it in a paper of Wei Zhang on Kolyvagin's conjecture in 2014. So the baby case of this already happens there. Okay, and then maybe the last remark I want to make is that, so of course, what Bloch and KATO tell you is that this inequality should actually be an inequality. And this I cannot prove, and you will see why, but I can at least give you some criterion. So you can establish a criterion. And maybe let me call this star, which implies that this star is an inequality. And this, yeah, I will tell you later what it is precisely. Okay, I think these are all the remarks I wanted to make. So are there any other questions about this statement?
It's actually just related to this side comment that you made. So you start with a Hilbert modular form, and it's not clear if you can construct an abelian variety. Is that because the Hilbert modular varieties are not curves?
Yeah, exactly. Because you usually want to do some Jekyll-Lagrange transfer to some Shimura curve, but it's not always possible. If you take something that has no level and your field is real quadratic, you cannot transfer, and then it's not clear how. Yeah. Yes. It's conjecture, but yeah, I don't know how to prove it. Yes. Yeah. So, for example, is this still here? Yeah. So it is conjecture. More precise that, for example, in this example, if your Fourier coefficients are integers, you should actually get an associated elliptic curve. And more generally, million varieties, but then yeah, it's not clear. Okay. Thanks. It is a very good question. Other questions?
When you say that F does not have CM, is that equivalent to saying that E does not have
Yeah, if
CM?
it comes from elliptic, again, if it comes from elliptic curve, yes.
Yeah.
Thank you. Other questions? Okay, so what do we do now? Yeah, so maybe I want to mention, of course, as we have seen from the conference, and there are a lot of works proving this kind of results. So I want to mention at least some. Of course, it's not possible to mention everybody, but I want to mention previous works using a similar method to the one I will describe. So this list is probably complementary to the one that Kim gave yesterday. So the technique I describe is a refinement of the method introduced by Bertolini and Darmon in 2005 in their study of the anti-cyclotomic Ramanujan conjecture for elliptic curves. And then so Matteo Longo did the same thing over totally real fields in the ordinary case. Then maybe there is also work by Hida and Shie for higher weight modular forms. Then there is work of Howard on bipartite Euler systems and work of Nekova. Okay, and as I said, there are many more people, and there are, of course, many other methods which have been discussed. For example, this recent work by Burungale and Flack actually proves some special value formula. Is one of the instances where you can actually prove something, not necessarily on a totally real or CM field. Okay, anyway, so let me tell you what was previously proved using such methods. So, what it previously was proved is the following: so that if the L-function is non-zero, then this Selmer group is finite. So this was proved under very mild assumptions by Nekova in 2012. Oh, is finite, sorry. Okay, and so what about the formula? So this formula star here was usually proved, but in the ordinary setting. This is what, for example, Matteo Longo did, and the point is that it's done via Iwasawa field.
Matteo?
Yes.
There's a question in the chat
Yes.
by Manisha Ganguly. The question is, when can one achieve?
Yeah. So I didn't mention yet. I claim that at the end of the talk I will mention, so that there will be a criterion. But yes, so you will see it as a byproduct of the proof. So at the end of the talk, yeah, you can ask again the question if you didn't understand it at the end. I didn't say it yet. Okay, so this will come. Other questions? Okay, so this is what people usually did, and in the goal of today, I just want to explain how to prove this inequality, at least. Let's say prove star more directly, by which I mean, for example, without going through Iwasawa theory. And the advantage is that in my theorem, I don't have to assume P is ordinary. I don't have to worry about splitting behavior of P, which other people had to do. The disadvantage, as I said, is that I cannot prove the full equality. Okay, so this is everything I wanted to say, and now I think I will try to describe the proof in most of the rest of the talk. Okay, so as I said, maybe let me mention it again. The technique is a refinement of what Bertolini and Darmon did. In 2005. And there is also another work which is quite closely related to what I'm discussing, which is due to Berti, Bertolini, and Venerucci, I think in 2015, where they also proved some special value formula, but in analytic rank 1 and over Q. Okay, and so I want to try to explain what's the point of this method. And basically, it relies on a dichotomy that already appeared several times throughout the conference. I call it a sign dichotomy. And I think, so for instance, this played an important role in the lecture series by Feng Liu. And then it also appeared in Lai's talk, Paul's talk, and Wei Zhang, for instance. So let me tell you what this is in our example. And I guess I have to make a table or something like that. So, all right, so I first fix maybe. So in this table, B over F will be a quaternion algebra. F is a Hilbert modular form as before, but with no restriction on the L function for the moment. And there will be an embedding of the units in K inside the units in B. Okay, so this sign dichotomy will be, of course, about the sign of the functional equation. And so there are two cases, which I will call the definite case and the indefinite case. Okay, so the definite case is when the sign is +1, and this happens precisely when the degree of the field is congruent to the cardinality, the set of primes dividing n, modulo 2. Okay, and this is equivalent, as I said, to the fact that the sign of the function equation is +1. All right, and so in each case, well, maybe the other case is exactly the opposite, of course. Okay, so now in each case, there will be a locally symmetric space I will work with. So what's the space? So in the definite case, I take B ramified at all places dividing n and at all infinite places, which of course is possible because this is happening. And I look at the associated locally symmetric space with full level, which I denote like this. But this is just a finite set in this case. It's very simple because the algebra is ramified everywhere at infinity, finite set. And in the other case, I take B, which is ramified at n and all but one infinite place. Using n. Okay, and attached locally symmetric space is a Shimura curve, it's dimension 1. Okay, and then the important thing, as I mentioned, is this zeta element. And this was actually already discussed in Wei Zhang's talk, so let me just recall it. So the point is that in the definite case, this algebraic part of the special value can be expressed as follows. So it's just the square of a zeta element that I will denote by zeta k. And what is this? So in Wei Zhang's notation, this is the integral k star of something I call FB. So FB is the Jacques-Langlands transfer of F to B. And this actually means just a finite sum of values of FB over Cn points inside B star induced by this embedding. Okay, so that's the first formula. And in the indefinite case, you have a similar formula, but for the first derivative. So maybe up to some constant that I don't care about. This is the Néron-Tate height. Of the zeta element zeta k, which in this case will be a Heegner divisor. And constructed taking linear combination of Heegner points on your Shimura code. Okay, so this is the key dichotomy, and somehow the whole method relies on switching from definite to indefinite case, as I will try to explain. Okay. Okay, so from now on, I'm trying to prove the theorem. So I will work, I want to assume that the L function does not vanish. So in particular, this sign of the function equation must be +1. Okay, and I fix some large enough integer, and I denote by a(n) of f the k to the n torsion inside a of f. Okay, and well, we want to prove this star, and the first thing which is easy to check is that it's enough to show same thing for this Selmer group attached to this. So let me write it. So the length of this mod p to the n Selmer group should be at most twice the periodic valuation of this zeta element. So the 2, of course, comes from this square, and this zeta k of f is the same as before, but I mean, in a few minutes, it will be important to keep track of the dependence on f. So let me call this star n, maybe. Okay, and now I need just a small definition.
One question.
Yes.
When distinguishing the signs, you say that F over Q is congruent to K mod 2. You said K is the number of divisors of the conductor?
Yes, so this degree, the definite case is congruent to the cardinality of the set of prime ideals dividing the conductor. Yes.
That's what I thought. Thank
And
you.
the other case is not congruent. Yeah. Thanks. Other questions? Okay, so a small definition. The prime ideal L inside OF non-zero is called admissible. And I will write L belongs to A if so there are a bunch of properties, and the maybe important one will be the very last. So L should not divide Pn. L should be inert in K. And then P does not divide the square of the norm -1. And most importantly, this is the last condition. So the norm of L plus 1 square should be congruent to the L Fourier coefficient of f square modulo p to the n. And the point is that this very last condition tells you that your L is a level raising prime. So this is what is important in the method, which relies essentially on congruencies of modular forms. And maybe a small consequence of the definition, which is not hard to check. So you can now look at homology of this an of f. Okay. So KL is the completion at the unique place above L. And this actually splits into a sum of two pieces. So the ramified part, this is U and R, plus a singular part, also called transverse part sometimes. And well, you compute that they are both abstractly isomorphic to Z mod P to the n. That's the first thing. And now I can finally maybe explain what are the key points key inputs of the method. So I will state the two key properties or constructions, and then I will explain how to actually achieve this. So here's the key construction. So take any two admissible primes, as in the definition, then we should construct two cohomology classes, C of L1 and C of L2. And so the key picture is the following. So we put C of L1 here and C of L2 here. Now those are, oh, sorry, this is a very bad typo. Those are global cohomology classes, very important. So now, because they're global, you can take the restriction to the composition group. For example, if you take C of L1 and you restrict at L1, they should land not in the ramified part, but in the singular part. This is the key point. Which is isomorphic to Z model to the Z. And the same thing for restriction at L2 of CL2, it should land in H1C. AN. So this is KL1, KL2, AN of F. Okay, and maybe, yeah, I can write this here. So inside here, you have the zeta element attached to F, and what you have to prove is what's called the first reciprocity law, which tells you that the restriction at L1 of CL1 is exactly this zeta element, except that maybe everything is only well defined up to a unit. So when I write equal, I mean they differ by unit. So res Li, C of Li equal up to unit 2, zeta element attached to F. So that's the first reciprocity law. And the second one tells you what happens if you localize or if you restrict C of L1 at L2, and same thing here. So if you restrict at L2, you will end up in the unramified part. And similarly here, you restrict this at L1. And again, as I said, those are abstractly isomorphic to Z modulo to the N. Okay, and now here, the important thing is what you see is another zeta element attached to what I will denote by G. And so what is G? Let me write it here. G will be a automorphic form, but for the quaternion algebra, which I denote by B L1, L2. So this is ramified at N, L1, L2, and at all the infinite places, and with coefficient in Z mod P to the N, and is congruent to F. Mod P to the N. So in other words, the associated mod P to the N Galois representations are isomorphic. So this is where you see congruence of modular forms arising. So let me write this second reciprocity law. It tells you that restriction at Li of C of Lj is the zeta element attached to this other form. Okay, and here I is different from G. So this is basically the first key thing you have to do, and it's the hardest one. And then there is an easier thing to do, which I will call B. So you have to show that this set A of admissible prime is large enough. There are enough admissible primes.
Data science.
Sorry. So yeah, there are enough admissible primes. What does it mean? That if you take a non-zero class just mod P in it, non-zero, there exist infinitely many admissible primes L such that, the restriction of your class at L is non-zero inside the ramified part. Okay, so those are the things you need to do. And maybe what I will try to explain now is that once you have A and B, somehow the method will give you this inequality I stated in a kind of formal way. So in principle, it could be useful in other settings where analogs of this picture have been established, like in the setting discussed in these lectures. Okay, but maybe before telling this, let me at least give you the rough idea of the construction. So you have to construct these classes C of Li, and as I said, the idea is that you should really look at this table and switch from definite to indefinite. So that's the point. So if you just replace n by n times Li, you're changing the parity of the number of divisors. So you switch from definite to indefinite setting. And as I said, in the indefinite setting, you have these CM points on Shimura curves. So you can use CM points on Shimura curve attached to the quaternion algebra where you add ramification at Li to construct C of Li. And the key point is that because I added the ramification, this will have bad reduction at Li. So this is why this localization does not land in the ramified part, but in the singular part. This is what is happening. And maybe just one word about how you prove the reciprocity laws very quickly because I'm late. So the first one, I will say nothing because it is what Yifeng Liu discussed in much bigger generality in his lectures. And the second one is where this Ihara's lemma gets used in a crucial way. And other than that, the key thing you need to do is you have to study, take this Shimura curve attached to Li, and you can reduce it modulo Lj. And the thing is that this contains, in the special fiber, you can find Shimura set attached to exactly the quaternion algebra, which shows up here. It will be the supersingular locus. And this is maybe somehow related to this geometric interpretation of Jacques-Langland's transfer, which was discussed in Prasanna's talk. Okay, maybe let me not say anything more and just try to explain you how to use A and B to prove the theorem. All right. So what we want to do is we want to prove this thing I called star n. So this inequality for the length of the mod P to the N-Selmer group by induction on the periodic valuation of this zeta element. So this is what we are going to do. So there are two steps. So first of all, the basic case. So we assume that this periodic valuation is 0. And then, well, if you want to prove the inequality, then you have to prove that the Selmer group vanishes. Okay, and yeah, maybe I will explain this because here is where you see maybe a baby case of what happens in almost every Euler system argument. So assume that is not the case. Assume there exists a class C in the Selmer group, which is non-zero. Okay, and now we just use A and B, and as I said, so B implies that there exists L admissible prime such that the restriction is still non-zero. Okay, but on the other hand, if you use this first reciprocity law, well, what does it tell you? So I can take this C of L, I can take the restriction at L, and it's here. So what I get is exactly this zeta element, and I'm assuming that this is a unit. But this is not 0 modulo P. Okay. And now what you do is you just use global class field here. So what you can do, I can take the sum over all places of restriction of C paired with restriction of C of L. And global class field theory tells me that this must be 0. All right, so this is a pairing Galois homology. But now another property of this C of L is that outside L, this is inside satisfies the local condition defining the Selmer group. And the same is true here by definition, and these local conditions are self-dual. So the only thing that survives here, I mean, there is no sum anymore. Only the term at L survives. So. Because only one term survives, this must be 0. Okay, but now, all right, but now we just check. So this is non-zero, and that's what we did here, and this is non-zero, like what I said here. And now the pairing between singular and the ramified part is a perfect pairing, and so this is a contradiction. Okay, so this is how you prove this part. Okay, and so far we didn't use the second reciprocity law yet, and this is where the most interesting part of the proof, and that's the last thing I will probably have time to explain. All right, so step 2. We have to do the induction step. So I assume this periodic valuation is bigger than 1. And then the claim is that there are 2 possibilities. First possibility. So either this Selmer group vanishes, or the following happens. There exist 2 admissible primes distinct, and G as before. Such that the following 2 things happen. So first of all, the periodic valuation of this zeta element decreases. So it's strictly smaller than periodic valuation. Yes. So that's the first thing. And the second thing you can prove is that the difference exactly matches the difference in length of Selmer groups. So maybe if you take the length is exactly equal to twice periodic valuation. Is minus twice. Okay, so this is what you prove, and maybe this is the hardest thing to show. But now, so if you have this, then you immediately get the theorem, right? Because you have the basic case, you want to prove the theorem by induction, And at each step, if the Selmer group is 0, there is nothing to prove because 0 is smaller than any positive integer. So you get the inequality you want. So maybe let me explain in the last 5 minutes or maybe a bit more why you prove this. And the important thing is that if you see this, perhaps you may imagine that you could try to prove the equality because the difference of length of Selmer groups, it really matches the difference of valuations of the algebraic parts of the special values, but I will explain why you cannot do this and where this criterion I mentioned comes from. Okay, so this is the last part. So are there any questions before? Maybe let me keep the key picture and also that. I'll just go here. Well, let me. This is what we are trying to prove. I'll keep it for a bit longer. So, okay. So I have to tell you maybe how you choose these primes whose existence is claimed. And maybe I will just tell you how to choose L1 because here is where you see the key point. So what you do is you pick L1 admissible such that the evaluation C of L1 is as small as possible. Okay, and by this I mean well the maximal exponent of a power of p dividing this element inside this cohomology group it lives in. Okay, so this you can do, and now the key point is the following. So you prove that if the Selmer group is non-zero, then this periodic valuation is strictly smaller than the periodic valuation of the zeta element of F. So this is the important implication. And the way you prove it is by adapting or maybe slightly changing the argument in step 1. So it's a similar argument. If you have a non-zero class here, well, there will be some prime L, let's say, where the localization is non-zero. And if you had equality here, you will get a contradiction. So this is similar to step 1. But the important thing, again, is that you really need this input. And then, once you have it, maybe the last bit, and then you're basically done. So let's move on here. So these are the key steps. I want to keep them. Let's move here. So maybe let me just say that once you have done this, you show also that there exists L2 different from L1 such that the following happens. So the periodic valuation of the zeta element attached to G is exactly the periodic valuation of this C of L1. Now you see why you need this assumption. So here you want this inequality to happen in order to perform the induction, and this is precisely what we got there. So this is smaller. So this is why the induction works. And then you also have to prove, of course, maybe you have to give a name. You have to prove this equality here that I will denote. Okay, and maybe let me just say without writing. So how you prove it? So here is where you have to use this second reciprocity law. So it's maybe quite a long computation. It crucially use this second reciprocity law, but other than that, it's just Tate global duality. The point being that you can explicitly describe the thermal groups of F and G, and the local conditions, they will differ in a very controlled way only at L1 and L2. And you will use like exact sequence coming from state global duality, relating strict and relaxed thermal groups. That's the key point. Okay, so maybe in the last 3 minutes, I can finally give the criterion I promised. So are there any questions? Basically, this is probably the end of the sketch of proof I wanted to give. So the last thing I have to do is just explain this criterion. And yeah, as I imagine, I will have no time to say anything about Ihara. Okay, so there are no questions, so let me just finish by emphasizing once more this. So what I described is enough to prove the inequality, but the problem is that if you want to prove equality, what you have to do is you have to rule out this possibility. So you have to show that if the zeta element is not a unit, then the thermal group is non-trivial. And these prove that what I called star is an equality. What you need is the following non-trivial existence statement. So if the periodic valuation of the zeta element is at least 1, then the thermal group is non-trivial. So that's, of course, a non-trivial existence statement of thermal classes, which you cannot hope to prove by what I discussed. Because mainly, everything I did so far involves computations with Galois cohomology. And so this means, yeah, my claim is that this is the criterion so basically the equality is reduced exactly to this statement here, which is in some sense the easiest possible existence statement for thermal classes, but still you need these non-trivial inputs. So maybe this is a kind of GL2 analog. Okay, and also, yeah, you will maybe to be precise, you will need this for F, for G, and yes, maybe for all the level raisings of F. So that's GL2 analog of Ribet's converse to Hart-Brown field. And of course, if you have the Skinner bound divisibility in Iwasawa theory, maybe you can deduce this, but without it, I don't know how to do it. And maybe, yeah, let me just stop here. Thank you very much for your attention.
Are there questions for Matteo?
So is it possible for you to say a word about the proof that this is the criteria for equality?
Proof that this is a, yeah, so we can just, so you just have, so if you want, you can do the exercise, go through the talk, you just check the proof with it. So suppose you want to prove that this star, let me rewrite something. So you prove that star is an equality. So this star was the thing in the main theorem. The assumption is again that the L value doesn't vanish, so you can still prove it by induction on periodic valuation of the zeta element. And if it's 0, that's exactly the baby case. This step 1 takes care of it. And now you just check step 2. So now, if this is non-zero, and if you have this, then this tells you that this exactly cannot happen. And so this is what will happen. But now, because this thing here is precisely an equality, you will know by induction maybe that this is equal to this. And then this equality will imply that this is equal to this, and you're done. The key point is that you have to rule out this.
Hi. So you mentioned you don't need any assumption on like any reduction type, right? I mean,
Well, I don't need an ordinary versus super
ordinary
singular.
versus,
Yeah.
okay.
Yeah, this it's it's
So
just because this is what you usually need to do this. Well, maybe periodic L-function and
Yeah.
stuff like that. That's maybe the advantage of what I was saying, that you just prove the formula over the base or the one inequality, and then, okay, maybe what you, one thing that you do need is absolutely crucial, and I didn't mention. So because the whole method relies on congruences, you need to have some description of the local conditions defining this Selmer group purely, maybe AN, purely in terms of the Galois representation. But in this case, it's fine because maybe a hard part will be how to describe the condition at P. And this can be done using like some finite flat group scheme. Finite flat group schemes. So the reduction should be good, this I should say. So, and this is what is explained in this paper of Nekovar, for example, some appendix. Okay, but other than that, we don't need anything. Yes, well, yeah, how do I say something quickly? So maybe okay, I will just try to say why it's important. Yeah, so do you want to know the statement, or do you want to know why it's important in the proof? What do you do? Why it is important? Okay, so let me try to say it in 1 minute, maybe. So let's just remove this. So the thing I didn't explain is how do you actually prove this second reciprocity law? So, and this is where, sorry, my notation is X. So what you have to do is, as I said, you have this is an I. You look at the special fiber at Lj, and now, and this contains well, the supersingular locus. And yeah, this geometric instance of Jekyll-Anglens tells you that this can be identified with the finite quaternionic set attached to this quaternion. So far there is no Ihara's lemma, but now what do you do? So essentially from here, you want to take Abel-Jacobi map and end up in H1 FLJ, and then En of F, which is just the ramified part of the homology. So this will be isomorphic to Z mod P to the N. All right. And so you get this map. And this is, I mean, there was a G in the statement, and it should be precisely a function from adelic double coset attached to this towards here, and this is my G. So the claim is that this is how you construct G, and the problem is that so you need to prove that G, I mean, in principle, just constructed a map, it could be the zero map, then you cannot do anything with it. So you have to prove that G is not zero mod P. This is a key point, and if you do it, then you get this second reciprocity law. And the thing is that now this can be reduced exactly to Ihara's lemma. For X, E star, and I. So I don't claim the reduction is obvious, but you can find it in this paper by Liu and Tian, I think 2020. Super singular locus in Hilbert model of varieties and level raising. They explain you why if you have this, then you can get that G is non-zero modulo P, and then you're done. So yeah, maybe you can ask me later if you want to know more.